morning, everyone. Welcome back. Um, so I sent you guys a link to reality capture. If you're not able to download it, don't worry. This morning I tried to go through it and take some screenshots so I can just show you. If you do have it, you can also follow along. But when we do the tutorial, there's one step which takes some time. So you probably won't be able to follow along in real time. In any case, before we get to that, there's a lot of theory that I'm going to cover. We're going to be looking at the basics of how photogrammetry works, and then what is involved in collecting data using modern data acquisition systems. And then we'll use some data. I'll send a link also for that data. It's just a sample data set from the reality capture website. We can use that to do a reconstruction. And then in the afternoon, after lunch, Dr. Jothi has arranged for a drone capture session. So we'll get to go and witness some data collection with a drone. All right, so let's get started. Photogrammetry, which is what we're interested in today, is a technique that uses multiple images in order to create a 3D reconstruction of a particular asset. So here's an example. You can see a house, and there are many pictures that have been taken around that house or cabin. And with those images, we're trying to distill out 3D information about the geometry, textural information about the surface of that geometry, as well as some accurate scaling of that geometry, so that we can have what is these days referred to as a reality model of that asset. And that reality model gives you a single reference, right? So it's useful because when you have multiple images, then each of those is a different view. And a single image will not tell you everything you need to know about the asset, because naturally there are going to be parts that are out of view in that image, and there are going to be parts that are more in focus. So images are good when you want to have localized information from a particular view. But if you want the whole asset, which is often the case when you're doing inspections, you want to get an overall view of the asset. For example, if you have a picture of just a zoomed in part of a structure which is not damaged, that is not sufficient to make an assessment about the whole structure. So that's why being able to put each of these images in context is a very valuable tool when we're trying to use the data that we've collected to make decisions about the integrity or health of an asset. So that's why it's important, and that's why we're going to look at different aspects of this. So videos and images are great and provide valuable information. Making measurements or understanding context is challenging in working with just images or video, but creating a model or structure can provide context and measurability. Now, the basis for photogrammetry is an algorithm called structure from motion. Modern photogrammetry packages have many bells and whistles added on, and have more sophisticated implementations of this algorithm. But it's still useful to understand this algorithm, because that can inform how we collect data and how we process it, even if we're using proprietary packages that are very common. So what is structure for motion? It involves these steps: feature detection, feature matching, sparse reconstruction, dense reconstruction, mesh generation, and texturing. So those are the steps involved. And this here we look at a representative pipeline. So I showed you an example of reconstruction yesterday in my introduction applications of computer vision. This is from that same paper, and you can see some of the pictures that they use, for example, to reconstruct the Colosseum. Here they were able to leverage several publicly available images of the Colosseum, and of course it's a very iconic structure, and so there were plenty available on the internet even back in 2006. But there are several challenges, as you can imagine, that are posed when you're trying to do a reconstruction from so many images taken at different points in time. The structure could be changing, the lighting could change, the camera properties are changing, and so on and so forth. But so all of those are factors that cause challenges. But the way that the first step in the structure from motion pipeline is identifying common features across images. So if you can build a feature descriptor that can identify common features across images, something that's sort of invariant to these changes, then you can associate commonalities between images and create sort of a graph of how images are linked to each other. But more than that, you can also precisely locate the points in the image, in a particular image that has correspondences in other images. Now, one way to do this is something called the scale invariant feature transform. And as I mentioned, the key thing about feature detectors is you want to have more and more invariances incorporated into this feature detector. In this particular feature detector called the SIFT, researchers developed a way to identify common features across images, even if they are slightly different scales. We're not going to go into details about how the SIFT feature detector works, but we can see how it manifests in the structure from motion pipeline. The SIFT features basically produce vectors that give you unique representations for interesting points in the scene. So what do I mean by an interesting point? It's a point where you have some change of intensity gradients. If you have constant intensity, then there's no gradient there. But if you have a corner point, or you have an edge, or you have some sort of features, or some sort of changing intensities, then those are potentially points at which you can find matches that can be used in order to align images together. So what this SIFT feature does is it produces a vector representation for each of the interesting points, and so there's a way to do that. And then if you have this vector representation, you can find vectors that are close to each other and have some threshold and decide that, okay, if these vectors are close enough, then they're likely the same point, even if they're in different positions. So that's the basic idea. So since then, there have been, of course, many other feature detectors that have been developed, which are more robust and more invariant, or faster to compute, but the idea is still the same as far as photogrammetry. These are some other popular feature types. SURF, for example, stands for speeded up robust features, which does it faster and more robustly, and you can read about those if you're interested. Okay, so once you've identified these features, then you're going to be matching features across images. The brute force way to do this is to take each pair of images and see if any features between those two pairs of images, or between that pair of images, are close enough that they match. Okay? And you do this for every feature in every pair of images. So that and that grows exponentially in the number of images and number of features, it can take a lot of time, but you can reduce your search space if you know in advance the order in which you've collected the images. You could build a system based on video, or if you have GPS coordinates of your camera locations, that also helps reduce the search space because there's some structure to how you're collecting the data, or the camera locations, and you can leverage that to your advantage. But then there's this very important step, which is using something called RANSAC, is random sampling and consensus. And what that involves is estimating something called a fundamental matrix between each pair. And so that allows you to see how one image transforms into another image. So it allows you to compute the transformation, and then you can see if that transformation is consistent for all the other matching feature pairs that you have obtained. And the way RANSAC works is it samples a random set of those matches, and then checks for consensus to see if the transformations between the pair of images that have been computed from some features match other features as well. And the transformations that are most consistent are the ones that are stored for the matching between that set of images. Okay. Here we have an example. We have these two images, and there are a set of features that have been identified in both of them, these features can then be used to align the images and determine the transformation. Now, an important point to be noted, and this is something that I briefly touched on yesterday, is that 2D images, they provide us with information projected on the plane, and we can use multiple images to infer the depth. Of course, from stereo cameras that if you have two pairs of images, then you can compute a depth map. So first you compute a disparity map, which compares the difference between the two views, and you then use that to infer the depth. And so here is an example of such a scene. But even if you don't have two cameras, you can still do this because we can leverage what we saw here, where we have features that are matched, to obtain correspondences between images, and then build up a similar problem to the stereo problem that you would have with two cameras, with just a single camera but multiple images, with some assumptions that the scene is static, we can use that to obtain this 3D information. So from a pixel position, we can get the location of a particular object projected onto an image. Now, if we have a camera center, then we can cast a ray from the camera center through the pixel position, and we know that the real object that was photographed intersects that ray. We don't know how far it is along that ray, but at least we know that it intersects that ray. So we know the 3D point is along the ray, but we cannot determine the depth. On the other hand, if we have another image, then we can get two rays, and we can find out where these two rays intersect, and that's going to be the point in 3D space where that object lies. So that brings us to multi-view geometry. Given projections of a 3D point in two or more images, our goal is to find the coordinates of that point in the world coordinate system. So in this case, say we use a feature detector to identify that this eye is here, here, and here, okay, then our goal is to determine that location of that eye, given that we know the pixel coordinates. The problem, though, is that we don't really know the camera centers either. So another problem is that even if you have two rays and you do know the camera centers, because of inaccuracies in the measurements, because of noise in the image and inaccuracy in your estimations of the camera pose, the two rays may not meet at the exact point. And so instead, we can reduce our error by sampling more points, by taking more images. And so we can set up the equations to solve for this 3D point in general, right? So if you have two rays, then you remember from last class, we can use the projection matrix to represent the relationship between this world point and the 2D points on the image. Now, for both these cases, if you're using the same camera, are the projection matrices going to be the same, or are they going to be different? Might be different. Why? The position of the object on the image plane might be different. Yes, it might be different. So, but why does that mean that the projection matrices are different? Camera positions are different, right? So the camera matrix has both the extrinsic matrix and the intrinsic matrix. It's the same camera. So what does that tell us about the intrinsic matrix? It's the same, unless you broke the camera in between the two points, or something happened, or if you change the focal length. But assuming that it's the exact same camera, then the intrinsic parameters are going to be the same. The extrinsic ones are changing because you're moving the camera. Yeah. So the rotation, the translation matrix, the translation vector might change, and so that's why we have P1 and P2. Okay. And just like last time, you can take this cross products and set that to 0, and that's the expansion of the cross product. I can rewrite x1 in this expanded form, and this again, like we saw last time, gives us two independent equations. So we have two independent equations in terms of the three unknown entries of x. What are the three unknown entries of x? The x, y, z coordinate of that point that you're trying to find. Now, the way we typically optimize this is to simply set up a nonlinear problem and then just use a solver to solve that numerically. There are other ways as well, but a simple way you can do it is just to set up the numerical optimization and solve it. So we're finding capital X that minimizes this function. So here we're regularizing a little bit to take into account the fact that if you have multiple images, multiple rays, they may not all intersect. So you're just trying to minimize the distance of the point of intersection. You're trying to find the x that minimizes this expression where okay. So I should have a description for what D is, but it's missing. So remind me about that later. I'll try to find that. But essentially, we're trying to minimize we're trying to make sure that the rays, the reprojection. Oh yeah, that's what it is. So this is the reprojection between x1 as you measure it in the image, and then when you project the point capital X back onto the image, then that's p1 times x, and then that distance you're trying to minimize. So you're trying to minimize that distance for all your images. That way, even if they don't intersect perfectly, you're still getting some reasonable estimate of what that is. Okay. So when we expand this out to multiple cameras, given a set of corresponding points in 2 or more images, we're computing the camera parameters and the 3D point coordinates. In the camera parameters, we can compute the extrinsic and intrinsic parameters if we don't know what they are. What is, so in this case, if we know what P1 and P2 are, then we can solve for capital X with just 2 cameras. So that's why in a stereo camera setup, you know the positions of the 2 cameras because they're next to each other. So if you have your coordinate system right in the middle or in some known position, and you have calibrated those cameras already, then you know the P1 and P2. So that's why you don't need to do any additional work to find what the depth is. But when you have a single camera that's moving, then that no longer holds true. So we need to also simultaneously estimate P1, P2, and X, capital X, at the same time. So how do we resolve that? We have more unknowns. So what do we do to figure out what those more unknowns are? What do you think? More images, so we get more constraints, and more images and more. We want to make sure we have more images of that same capital X. That's important, right? So you want to get the same capital X from multiple views, and you can also get different capital X's. And why would that be useful? If you get more capital X's, you get more 3D points. So if you get more capital X's, then you get more constraints for your projection matrices, right? But you also get more unknowns because there are more capital X's. But those can be useful because you do want to obtain a dense reconstruction of the scene, right? So you get more X's and you get more camera poses, and then you jointly optimize. So in general, we're just doing the same thing where we are minimizing the reprojection error, right? We have some estimate of capital P and we have some estimate of capital X, and we are minimizing that reprojection error. Now, since this is a multi-view problem, when you have opaque objects, there are going to be occlusions, right? I cannot see the door there if there's a door. because it's blocked, but you can probably see, right? And so not all capital X's are visible from all the images that you take, and so you need to appropriately account for that in your objective function, where you switch on and off function for certain images and points. Okay, so once you solve this problem, you get a number of capital X's, and you get all the camera matrices. And then you can do something called a densification, and we'll look at that when we look at the tutorial. But that allows you to get more capital X's if you need that for your problem. And then once you densify your model, you can start to create meshes and textures. So one commonly used approach is something called a Poisson reconstruction, where you identify a surface based on the points that you have obtained based on a manifold that is close to the interface between what is inside and outside a region. And that is something that's typically employed in most photogrammetry packages, and that allows you to create the mesh representation. And then I don't have a slide for that, but there's the last step is to superimpose the texture onto the mesh. And the way that's typically done is through something called UV mapping. A UV mapping gives you a mapping from 3D coordinates to 2D coordinates. So if you do a UV unwrap of a mesh, then you can lay that mesh out in 2D, right? So if you have a cube, that's a 3D object, but I can cut, say, imagine it's a cardboard box. I can cut out the edges, and I can make it, look like something like that. Okay, maybe I can use a marker. They gave me one, and I said I didn't want it. Okay, let me just try. No. Okay, it's having some problems. Can everybody see this part? So if I have a cube, then I can unwrap that to look something like that. Right? And now what I can do then is, say I have some images of the cube. And say I have more images. Then I can take atlases, right? I can take this bit and I can stick it here, and I can do the same thing for other faces. I'd have to project them, and so there are algorithms where you can you already know the correspondences because you have the calibration and you have the points, so you can do that. But there are some algorithms to decide which images to use and which parts of the image to use. And then those atlases are blended using some blending methods. And it reconstructs this 2D thing. And in most packages, you can find this 2D file. Maybe there are thousands of small 2D files sometimes. And then it's just easy to reproject back onto this 3D surface. So that's how it works in most computer games, or in most anytime you see something that is photogrammetry based. That's how the texturing is done. Okay, seems like my computer is having internet connectivity problems. Okay, seems like it is connected. So let me see if slide is moving. I think I need to. All right. So once you do that, then you can get textured representations that you can visualize. Now, the source of this texture are the images, but there's some blending that occurs, and there's some averaging, and so if your alignment is not perfect, that can cause some distortion in the textures. So that's why it's always a good idea to use the images still, even after you make the reconstruction, because that way you have the original source of your data. And if you need to see fine details like cracks, it's going to be easier to see them in the image. But still use the 3D model and the texture as way to navigate the data set that you have collected in a structured form that is very much like the asset itself. Any questions about the photogrammetry process? Well, you need to do the photogrammetry process first. So you need to figure out this UV mapping, right? For a cube, you can do it. So if you have a simple cube, you can kind of code this up. But if you have a complicated structure, then it's harder to do it sort of procedurally. So you have to use automated algorithms, but those algorithms rely on you having the correspondences between the points in the scene and the camera locations, right? You need that, otherwise you can't do this atlas map. So I'm saying you need to do the photogrammetry first. You need to know for your mesh model, you need a UV map, okay? So that gives you 3D to 2D correspondences. And then from your image, you need to know which part of the image corresponds to which part of the model. And then you need to sample that image and apply it on the UV map. Does that make sense? So all of these photogrammetry packages, all of them do that. And there are open source ones as well that you can use. This Alice Vision Mesh Room, which is what I have on the screen, that's open source. It's based on OpenSFM. So you can start from there if you need to. Other questions? So that's a good question. Are there intermediate steps to convert a mesh model to a BIM model? That I would say is an active area of research. people have proposed some automated, some semi-automated processes, um, and also people usually use it as a reference, because if you have a mesh model, you can import it into Revit, and then you can use tools like there's this tool called Dynamo where you can create things parametrically, and you can get it to match by visually looking at it. So there are some assisted ways that you can do it, but also you can use, you don't necessarily need the mesh. Even from the point cloud, you can use, or people have been proposing deep learning methods where you can extract coordinates of the section, and then you can extract the elemental connections. So we worked on, I'll talk about this tomorrow, but we worked on one way to do the instance segmentation of a bridge point cloud. Why is that? So what is instance segmentation? It's where you identify every instance of a particular type of semantic information class. So in a bridge, you have many components. So you have many girders, you have many piers, you have a deck, you have some railings, guardrails, and you have pier caps. If you can identify exactly which points correspond to pier cap A and pier cap B, and pier A, pier B, pier C, so on, then you can use that point cloud information to build the connectivity, the element connectivity matrix. And then you can also, for each of the elements, identify its section. Then you extrude, and then you create a CAD or BIM model. So that's kind of what people have been working on. I'll show you one example of the instance segmentation tomorrow, but it's still kind of an open area of research. So ideas, I think, are welcome on how to do that. Yes. Yes. Yeah, it's a good question. Of course, with the photogrammetry process, you can only reconstruct what is visible in the images that you take. It is possible to construct reality models of indoor scenes as well. The same processes that we described will still work indoors. So if you take many pictures of this room from standing and moving around, you should be able to reconstruct this room. Now, it is challenging to have, if you want the entirety of a building with one scan without any manual intervention, that I think today is still challenging, because at the interfaces between rooms, there's a very high rate of change of what things look like. Because when you go through the door, as soon as, if I'm standing here near the door, then everything on that side is totally different from everything on this side. And small changes in views cause, small changes in camera orientations cause significant changes in the views. And so capturing those interfaces can be challenging. That being said, it's not impossible, it can be done. You just have to pay a lot of attention. A simpler method might be to just do all of the rooms and then to manually associate them into their proper positions, or to do it in some semi-automated way. Another thing that's very common on construction sites these days in the US is to have markers, and you identify the locations of the markers in advance as soon as you place them, and then you can use those markers as control points that can help you align the indoors, the rooms, more efficiently. So hopefully that gives you some ideas. But yeah, in general, of course, you cannot reconstruct things that are not visible in the image. All right. Any other questions? So then we can move on. I do want to come to these. Yeah, actually, let me do it in order. So now let's look at different ways we can acquire data for photogrammetry. These days, there are many remote acquisition platforms that can be used to collect data, and these can be operated manually, or they can be operated autonomously, or they can be programmed to follow some automated path. Depending on what kind of structure you're looking at, and depending on how frequently you need to be collecting that data, and depending on what kind of sensors you're going to be using, you can decide what platform would be useful. In general, I have 4 categories of remote acquisition platforms that can be remotely operated. These include unmanned ground vehicles. These are particularly useful in construction sites. Terrestrial robots also would be a part of type of unmanned ground vehicle. Then you have drones or unmanned aerial vehicles, and then you can have unmanned underwater vehicles as well. Another remote acquisition platform would be manual collection, like have a person going in and collecting data. That's still very useful, very important, and is very good to supplement things that might be hard to reach with these remote acquisition platforms. And there are also many different sensors that you could use. There are DSLR cameras. They have their strengths and weaknesses. If you have a variable focal length DSLR, that's not so good for photogrammetry, because that's the fact that the focal length can change. So you don't want to use fixed focal lengths as much as possible, because that simplifies the photogrammetry process. You can use mobile phones. They work really well. You can get GPS data as well with your images, and that makes it faster to collect data. You can use 360 cameras. 360 cameras have some distortions, but you can undistort them. You can also subsample from those cameras. And so a 360 camera takes 2 equirectangular images. So it's like it has 2 lenses, one in the front, one in the back, and it takes a hemispherical photo, 2 hemispherical photos, and then combines them. So when you take a picture, you can see the whole room. Now, the disadvantage of a 360 camera, apart from the distortion, is that even though you're capturing the whole room, I'm not capturing the whole room at the same resolution with one picture, right? Because even though I'm getting a picture of that wall, the resolution of that is much lower than the resolution of this part. So you still need to, collect data from all the points as you would with a regular camera, except that now you're getting more data from all sides. Total station. So can photogrammetry be used for accurate surveying? It can be, but there's some caveats. You do need some sort of referencing, and so typically that is done either with LiDAR or with some traditional surveying methods. So LiDAR is light detection and ranging. So you have, similar to total station, where you have a laser. You have a laser that goes, but here with the LiDAR, you have many many beams that are cast, and then you get the reflections from all points, and that is much more accurate because it's measuring the time of flight of each of those rays. So you can get a much denser and rich set of points. But so what is typically done with photogrammetry is, and I'll talk about that towards the end, is to use something called a ground control point. And those ground control points are points for which you know the XYZ coordinates very accurately. Maybe you can get 6 to 15 of those for your photogrammetric survey. And that references the points that you have identified by photogrammetry. And because that is reference, that allows you to scale your photogrammetric reconstruction. Now, if you have very accurate camera positions, right, say because you have a very accurate RTK GPS, then you can get away with not using the ground control points, relying on that GPS data. But again, even modern RTK GPS systems, they're not going to be as accurate as having really good ground control points from traditional surveying. Okay. So there's synergies between these approaches. It comes down to what you're looking for, right? How accurate do you need the model to be? There are also other challenges with photogrammetry that are separate from the ground control points, because we're doing a bundled adjustment and we're simultaneously determining the camera positions and the 3D points. That nonlinear optimization may result in some drifting of estimates, and that may warp your whole scene. So that's sometimes a problem with photogrammetry, but there are some undistortion methods as well that can be applied, and these are also available in many of these proprietary packages, including reality capture. So there are, if you know surfaces that should be planes, then that can be useful in making sure that your model is not warped. Yeah, I think so. I think it's there's nothing too complicated about the math behind this, or just using the software is also quite simple. So I think it's a good idea. Okay. Where was I? I was talking about the camera sensors. Of course, there's the 360 camera. There's also RGBD cameras. So these function in different ways, but essentially they produce a depth map, and they can be of varying quality and varying accuracy, resolution as well. But when you have RGBD cameras, they work, they give you additional information about the scene that can further speed up the process of creating your point cloud, because you already know the depth of the points in the scene. So that's very useful data for our photogrammetry process. So there are softwares that take into account the depth as well. And finally, you can use onboard cameras. Most drones have cameras that are equipped to do photogrammetry very well. So those are really good options when you're trying to create a reality model of NASP. Okay, so once you've selected your data acquisition mode and your sensor, then you have to collect data. Before I talk about how to plan that data collection, I want to tell you about different data acquisition modes that are typically available. So you have manual missions, automated missions, and autonomous missions. In a manual mission, this is required for most civil infrastructure surveys, except on construction sites you can kind of automate things. For bridges, if there's no traffic, you can use automated things, or if for buildings, if you're flying much above where pedestrians are going to be, then also you can, there are no obstacles, or if you have really good obstacle avoidance, then you can get away with using automated missions. But in most cases, you do need some manual flying. So of course here it's controlled by the pilot. So the pilot has to take into account many things. They need to take into account where the drone is, or where the robot is, and how far it is away from the structure. They need to take into account where the camera is looking, because that is also going to be manually controlled. And they need to take into account where the obstacles are. So it's a lot of work mentally as you are flying. So you want to observe the scene as much as possible, and decide all of these things in advance. So when you're actually flying, you can just worry about not hitting things. Right? Because if you're thinking about all of these things when you're flying, then that makes sense. Another challenge when you're doing a manual flight is it's difficult to ensure coverage, because if you're flying manually, it's difficult to control drift, and it's difficult to control the exact height. You can use the altimeter to get some sense, but you want to compute those things in advance. You do get more fine-grained control, but if you're trying to get into hard-to-reach spots, then you need some skill as well. It's difficult to change the camera while you're flying. This is possible to program in automated missions, but if you're doing manually, typically you just want the drone and the camera to look at the same spot if you're trying to cover. It's ideal for use in cases where automation is not an option, and for small areas that you can look with. The next method is automated missions, and these are also called pre-programmed. And this is the example that I showed you last class, where the drone was controlled predominantly by GPS. Now here as well, you can also have obstacle avoidance in addition to GPS navigation, and that's a good combination, because then even if there's something in the way, it's not going to ram into it and crash, but it can at least attempt to move around. A waypoint is this GPS location that you provide that the drone needs to go to, but it also includes the point at which the drone needs to be looking at. So if you remember the purple and blue balloons. There are different modes. So there's waypoint mode, where you specify each of the waypoints. There's also a horizontal mode, where you are doing a fixed pattern, and this you can do at a single plane. And even if you do it at a single plane, you can reconstruct a 3D representation of the area, because you're getting multiple views. And you can typically, this is done with an oblique camera, so you can also see the sides of structures. If you only have a view looking down, which is called a nadir view in geosensing, that makes it harder. But you can also combine multiple views, and those are studies that you can do based on what type of asset you are trying to capture, to determine what mode would be best. And for buildings or tall bridges, you can also do a facade scanning, where you go up and down. It's always nice to have regular patterns. Why? Because if there are people around, then they can have some predictive capability for what the drone is going to do next, right? So that is always reassuring. Also for the pilot, it's easy for them to check if the drone is doing everything correctly. And also the images are orderly, so it's easier to use later on. For objects that are symmetric, you can also have circular paths. So this gives you a slight change in views. In general, it's preferable not to have views exactly parallel to the surface. So even if you have this lawn mowing pattern, ideally you want to change, offset these views a little bit, or have an oblique camera so that it's not exactly parallel to the surface. But with the circular path, you can still look at the center, and you can avoid having to move the drone off the path. So I showed you an example of a waypoint mission already. Here is one path where you can see the different aspects of a waypoint mission. Again, this is using the Litchi app, which works with some DJI drones. And for tall structures, of course, you can have multiple loops around the structure. And it's important to be able to maintain the line of sight, right? So if you're standing somewhere here, then you can walk from here to here, and that gives you some view, but you can't really see the back, so you don't want the drone to be flying there. But you can still get some of these views without going behind the structure, and so you can try to work with all of that. I showed you this example already. You can see the drone there flying as well. So these are some autonomous, or these are automated scan or automated and autonomous scan modes from different providers. The DJI drones, they have some of these. They have the automated ones, the waypoint, orbit, panorama, but they don't have 3D scan. Actually, the 3D scan is only available with this Skydio, which is an American company. And we can see how that is different from these automated modes. So let me show you a video for that. Let's see if I can get this to be clearer. Maybe I need to, oh, sorry, you're not seeing this. So here is an autonomous scan mode, and what happens here is that the drone flies by itself. Let me see if I can get a better view. So the drone creates a 3D map of the environment as it's flying, and then it navigates itself in that environment. And as it does that, it also computes how much of the 3D volume it has covered. And by doing so, it mitigates a lot of the work that the pilot needs to do. And the way it works is it has 7 cameras that take pictures of the surroundings, and those 7 cameras are used to triangulate in real time everything that the drone is seeing. And at the same time, it's also mapping that out. Let me see if I can find a better video that illustrates that. So I think they had one on let's search for Skydio 3D scan bridge inspection. No, that's it. So you can see the drone there. And so you can see here how it does it. So let me pause here. So you can see it says scan in progress. It's taking this picture and it's seeing, it's identifying what aspect of that image it can add to the coverage. So that's what you're seeing here in purple. And let me see if I can find. Okay, let me play it. And you can see the obstacle avoidance is really good. So it can get into these tiny spaces, and the camera can look up and down and sideways as well. And you can see the views from the navigation cameras here. So you can see the 6 cameras, and then there's a camera that's used actually for the data collection. But you can see how it maps all of these views, and it creates a map of the scene, like how we saw with photogrammetry, but it does it in real time using some proprietary deep learning techniques, I suppose. And it's pretty reliable. We've used it a lot over the past 4 or 5 years. And anyways, so hopefully that gives you some idea for that. Now the way that you set this up is you need to define a scan volume. So you go into your app, and then in augmented reality you set up at least 4 or at least 3 columns, and then everything inside that column is the scan volume, and then the drone flies to survey the scan volume, and it creates a low density map of the scan volume, so it knows where what is. And then it tries to make sure it creates a plan to cover everything in the scan volume, and then you can start the mission, and it goes and collects all of that data. So of course there are some challenges. You should not be using it if there are moving objects. So if there's traffic, then you can't use it because it cannot react fast enough. It's not as good as the self-driving cars. And also if you're flying over water, then the cameras don't function as well. So you need to be careful. But I'm sure this will start appearing in more drones soon. But right now there's just this one company that makes these. Now we've used this a lot, and you can set different scan parameters. For example, if you're doing the underside of a bridge, then you can use a 2D upward scan mode. So you do the same thing, but you set a plane, and then it does that plane. There are many parameters that you need to take into account when doing these types of scans. For example, you can decide whether or not you want to stop for a photo, or you want to take the photo as the drone is moving. I don't know if you can see, but here, if here I can set things like the overlap that I want in the different directions, which is a very important factor for photogrammetry. I can set that. I can see how long the scan is going to take. I can set the height of the plane, and I can set whether or not I want to do hatch in X and Y direction, things like that. And the reason you're able to do this is because it has the volume at which it needs to be scanning, and then you just set the plane and you can do that. But here we've chosen the stop for photo option, and you can see that when you choose that stop for photo, it takes longer. It's like 10 minutes more for your scanning time, and that's a big consideration when you're out in the field, because you may have limited batteries for your drone, and a drone battery life maybe is 25-30 minutes or 40 minutes, and so you have to factor those things in when you're planning things out. So you want to take as much power with you as you can, so you can do all of that. So in general, when we're trying to develop these photogrammetric reality models in practice, there are different steps. The first step, like I said yesterday, that is most important, is to identify why you're building that model. Because if you don't do that, there are too many unknowns. But if you're building a model, you should know why you're building it anyways. And then you can decide what to do. Then you do the data collection, you do the data preprocessing, you produce the reality model, and then you get your outcome, which is whatever objective you want, and then you verify that somehow. Now, for the data collection, when you're planning the mission, there are many steps that you need to do. After you select your outcome, then that will allow you to determine the resolution of data that you need. And once you determine the resolution of data that you need, then you can choose the platform that you want to use to collect that data. And one important parameter that you need to compute is the distance to surface. How far do you want your data acquisition platform to be from the surface? So what are the different things that influence that decision? What are you looking at, right? So what's your objective? What are the features you want to identify? And then what? So level of detailing is a term that's used to describe how detailed your representation of a particular asset is. And so, for example, if you're generating BIM models or CAD models, then LOD is a terminology that's used to see how detailed your CAD representation is. So if you have just a box, that would be, the lowest level of detail. But if you have everything with all of these grooves and the door handles and this water bottle all in place, then that would be a very high level of detail. So that also will influence your distance to surface. What else? So environmental considerations that may influence your data acquisition platform, like interference from metal or wind, all of that you can use to add to a factor of safety in how far you are from the surface. What else? Rules and regulations, very important. That also has to be factored in. And I think we covered most of them except maybe one more important one. So I was looking for the camera, right? Because it depends on the focal length of the camera. If you have a very large focal length, then you need to be further. Okay, so then you determine the distance to surface. I'll show you some ways to compute what that is, at least based on the camera and based on the resolution that you're looking for. The other things are just things you need to check for. Then you need to partition the structure so that you can determine your flight modes for each of the partitions, because civil infrastructure again can be complicated, especially bridges. For buildings, maybe you can have a single flight mode, but for bridges, that's usually not easy to do. So you need to partition the structure, and then you have a different flight mode for each of the partitions. And then you need to check the service and traffic if you're doing bridges, or even if you're doing buildings, you can do that. You have to check the service and traffic to see what moving obstacles you might encounter. And then you apply the rules and regulations, and then you modify your distance to surface. Then you choose your flight modes, and then you get your flight parameters. And then you do some pre-flight checks to make sure everything is okay, and then you can fly. So the distance to surface is the factor that you need to determine when you're flying the drone. So you need to compute that in advance. And this is basically the distance of the camera from whatever you're looking at. So if you're doing a nadir flight, then it's the distance to ground, or the ground surface distance, or ground sampling distance. And if you are looking at a vertical surface, then it's just surface. So this is typically measured in real world units per pixels. So how do you compute that? Well, we can use our camera model. There are different ways you can compute it, but one is if you have the resolution and then you have the ground sampling distance that you need, then you can use that to compute the distance to surface. So say I want to be able to find a crack, right? And so assume that we want to see a crack of at least 0.5 millimeter in width in our image. And then we want there to be at least 2 pixels for that crack in the image that we take. Okay. So now with that information, if you know what camera that we have, then we can compute how far we need to be from the surface to be able to take that picture. So how do we do that? We can use this figure. We have the horizontal field of view divided by the sensor horizontal width, which is SH in this case, times F is equal to this working distance, which is my distance to surface, okay, just from similar triangles. So for example, for a DJI P4, if I have my horizontal resolution of 5472 pixels, and then my focal length is 36 millimeters, my sensor width is 6.4 millimeters, then I can compute the distance to surface required as 5.13 meters. Okay. There's another way you can compute this, which is using the degree field of view. Instead of using the horizontal field of view, you can use the degree. And in that case, typically what is done is to take the hypotenuse of the image resolution. So for example, for the Skydio X10, the resolution is 6944 times 9248. And so the diagonal resolution I will get just by taking the square root of the sum of squares. And then I multiply that with my crack width resolution. Say, for example, I'm looking at 1.27 millimeter width cracks because I want to figure out the condition state. So that's defined in the Astro manual. So then I can compute how far I need to be, and that would be I would use the tan of DFOV over 2, right here. It's the same thing, and then I can compute the distance to surface. And then we should apply a factor of safety. So in this case, so there are different factors of safety, right? There's factors of safety to make sure you are far enough away from the surface so you don't crash into the surface. There's a factor of safety making sure you are close enough to the surface so that even if there's some motion blur, you still capture the crack. So if your concern is that the crack is going to be really small, then you want to get closer than what you compute. If your concern is that you're going to crash into the wall, then you want to be farther than what you compute. Okay, and there may be a limit to what you can measure given the rules and regulations, and then in which case you need to change your camera or find some other way to get that. So in this case, if I'm worried that my crack is not going to be visible because the drone is moving, then I can, instead of 15.75, I can get closer and take the data at 10.5 meters from the surface. Okay. Any questions about that? So how much time do we have? 7:15. Now this calculation is not something that you have to do. Most manufacturers, they give you this table, right? So you choose your ground sampling distance, which is the resolution that you need, and you can just get the distance to surface from the table from the manufacturer. So we did some verification of this just to make sure that it's accurate. So what my student Reza did is he took our drone and then he found some cracks of sizes that are mentioned in the Astro manual, because this, from the manual of bridge inspections, it delineates condition states of certain members. It's different for pre-stressed concrete and different for reinforced concrete. And at those thresholds, the lowest thresholds, we try to take pictures at different distances of a crack and see if it's still visible in the image. So it's a very simple experiment. You can see, well, it's hard to see here. Let me zoom, maybe. You can see the cracks, right? You can see the crack in the image from his phone. And you can see that at 3.5 feet, all of these cracks should be visible from the camera, and indeed they are, right? It's a little blurred because of Teams and because it's a screenshot, but you can see that there's a crack, and you can see here also that there's this crack, right? But as you move away, then you're not able to see it in the image anymore. So here, even if I zoom in, you're not able to see any crack in the middle. And it's the same here. So even though the crack exists, you can't see it in the image. Why? Because you're too far away. So this theory is, of course, very valid and easy to validate. And it's important to take into account based on what you're trying to achieve. Okay, so you should choose platforms that allow you to get to where how far you need to be from the surface. Platforms and sensors, right? So it's even though I put them one after the other, it's a joint decision that you need to make. And there could be many options based on what you're trying to do. Of course, anytime you're using an autonomous system, your safety and the safety of those around you and the safety of the infrastructure should be your top priority. It's very easy to crash. In the US, you need to make sure your airspace is approved for the type of flight that you need to be doing. I don't know the rules here, if it's similar. Red zones and green zones. So the drone can't fly in the red zone. DJI, yeah. So DJI has that feature. So that the simple rule is 5 miles from an airport in the US. So the DJI, if it's more than 5 miles away from an airport, then you can fly. If it's closer than 5 miles, then you can't. Is it similar here? Is it based on the distance from the airport? Is it 5 miles? Do you know? Yeah. Okay. Yeah. Yes, it's the same. So if in the US you cannot fly above 400 feet unless it's a Class E airspace. Well, unless it's a Class G airspace. I'm sorry. So Class G, you're limited to 400 AGL, 400 feet above ground level. But if you're flying above a building, then the ground level is the top of the building. So you can fly above, provided you're not clashing with the restricted airspace, which is where airplanes can fly. So you need to become a pilot if you want to fly a drone commercially. I have a commercial pilot's license, and so I can fly. But you need to take a test where you understand all of these airspaces, and then you need to request for authorization through an app, and then you get the authorization. So you need to submit your flight plan as a part of that. So you need to say where you're going to be flying, how long you're going to be flying, what altitude you're going to be flying, and what kind of flight modes you're going to be using, and how you're going to be observing the drone. All of that information you need to submit, and then you get approval, and then you fly. And then yeah. So it's a good system, I think, because you don't want to be crashing into planes. and even though it seems unlikely, it's quite possible for that to happen. Yeah. So anyways, the point is, before flying, you need to take into account aviation rules. But apart from aviation rules, if you're looking at particular assets, those asset managers may also have rules. So in the state of Texas, the Texas Department of Transportation has strict rules for the use of unmanned aerial systems. So these are more rules that you need to be following. For example, you need to stay at least 50 feet away from rail crossings. When flying, you need to be at least 50 feet above roadways in which the speed limit is 40 or greater miles per hour. And then you cannot take off or land between lanes of a highway. And you need to stay at least 20 feet away from main expressways. So those are the kind of the main rules, but there's more. There's a whole manual for. So you need to make sure that when you're planning the flight and you're setting your objectives, you can still meet them despite meeting these rules. Otherwise, you have to change your mode of data acquisition. And so that's why manual data acquisition is still important, because it's very difficult to meet all of these rules and have an automated mission, unless it's so important that you can stop traffic, and then things become easier. Okay. Now the next step, like I said, is to partition a structure. Now, depending on what kind of structure you have, you can partition them in different ways. So here is one way we partition this Main Street viaduct. So this is a historic bridge. It was built in 1914. It's a very nice bridge in downtown Houston. It crosses Main Street and Buffalo Bayou. So the bayou has been removed, but you can see the partitions that we made. We had one for the left portion, one for the right portion on both sides, and one at the top, one for the front, one for the back, and one for the bottom. So you can see how many different flights you need to be doing to capture everything that this bridge has to offer. Here's another example. It's a small truss bridge. So here, this was in a rural area in between Houston and Austin, and it has very low traffic. So its average daily traffic is 60. That means in one day, 60 cars will cross this bridge. Okay. So we got permission to do autonomous scans on this. We still had a DOT truck that was on either side with lights on, just for the chance that somebody might come on the bridge. But even then, even though we were doing a 3D scan, because of the size of the bridge, we had to partition the 3D scan. So we started off doing just 1/4 of the bridge, and then we added another quarter, and then we got more confident and we did a half of the bridge. So with this 3D scan, all we have to do is set these 4 pillars, and then set the distance surface, set the overlap, and then we just let it run. So it's much simpler than doing all those things. But even after that, we did another scan, which is just to make sure we get the top side. We did a 2D, or actually no, we did do a 2D capture, but that was just to get the surrounding areas. It's not in this. But we did some manual side scans, and we did a 2D upward scan. So the 2D upward scan gets the underside of the deck. So any guesses as to why we did the manual scans in the side? Because of the trees? Not because of the trees? Not because of the wind. It is more to do with coverage. So for the 3D scans that we did, we excluded the underside because we didn't want the drone to be flying above and below the bridge, but we wanted to have it just above the bridge so we can see it at all times. So we just did the top, and then we're doing a 2D upper scan of the bottom. Now these are disjointed scans, and we want to be able to tie them together. And so the easiest way to do that is to have a few oblique views of the side and bottom and the top. And so that's why we did a manual scan of this. Okay. Another reason is because a very important part of the structure, which is a truss bridge, are all the connections. And those connections, we wanted to make sure we get the full resolution. So while we can do this sort of scan to get the photogrammetry representation, when we wanted the details of specific members, the best way to do that was still to fly to those points manually and collect those specific pictures. So it's still useful to have the photogrammetry because then you can put all of those things in context. So that's why those are the two reasons why we did the manual scans in the site. Any questions about that? This bridge is not so wide, so and also this drone has visual inertial odometry, so it can use, even though it's flying over water, because it has the deck, it's able to navigate. So even though the GPS may not be as good, because the bridge is not so big and because it has the vision-based navigation, it works okay. It may not be the same if there's no visual navigation. Now, another important parameter, I briefly touched upon this, is the image overlap. Should I pause now, or should we? Yeah, okay. Let me pause now because it's past 11:15, and then we can continue after the break.